Hey guys, welcome to probably the last video on chapter 8 before we do some of the homework questions. So the first thing we're going to talk about is 8.6, which is conservation of energy. Conservation, oops, conservation energy. Okay, so basically what they're saying there is in a system, like in like when a car is driving or when I'm running or when a bird is flying or something like that, that they're saying that energy cannot be created, created or destroyed. Whoops. Sorry about that. Destroyed. Um, and what they're saying by that, destroyed. Oh, I think the screen cut off there. But but then, what does that mean? Well, where would energy go then? I mean, it can be converted into other forms of energy, other forms. So let me go through. I mean, we have kinetic. There's some forms of energy. Forms. Kinetic. Potential. That's a little different color. Potential. Heat. So thermal. Thermal. There's all different types of forms of energy like that. And so um, what you need to think of when we're talking about conversion, I like to picture like a car moving or a car, working its engine really quickly to move or so you can look at page 110, you have up there that little wind up car. And what they're saying is, well, it's moving and it's expending energy basically. So it had before it started moving, it had 10 joules of potential energy, right? Because the spring holds that. It has 10 joules. Oops. 10 joules PE. And then it starts moving, and PE, potential energy, goes to KE, kinetic energy, right? So you have that big arrow. But then you see it only goes to 8 joules. 8 joules of KE. Well, it looks like 2 joules of energy got destroyed. But that's not possible, right? So it actually, 2 joules of energy was converted into heat. 2 joules of heat. 2 joules heat or thermal energy, right? And so, I mean, you'll notice the engine, that the motor or the spring, it'll get hot, it'll heat up. So that's why, your car, it your car actually it's much more complex than this little wind-up car. There's a lot of different outlets that the energy goes to, so you're not using very much of that energy as kinetic energy to actually move. There's a lot of different things like your air conditioning. That's an off branch of the energy and stuff like that. But in this little car, excuse me, in this little car, we have 2 joules that off branches heat. So that little gear system in the motor and even the wheels, they're heating up because of friction and just just that's an off branch because 8 plus 2 is 10, right? Conservation of energy. So that leads us right into machines, which I think is probably one of my favorite chapters. Sorry, one of my favorite topics in all of chapters 1 through 8 for sure, 1 through 10. I mean, when we get to uh, waves and electricity, that's a different story. But and machines are really cool. Basically, machines. Let me just get a little title. I can do one of my off-branching things again. Machines. So I think machines are, as I said. So let's just read the first sentence, just so I can give you a really generic definition for machine that I might not be able to give you otherwise. A machine is a device used to multiply forces or simply change direction of forces. So that's pretty simple. It's like if there's this big boulder, oops, big boulder, and I'm standing over here, and there's no way I could lift that, right? I'll try as hard as I can. There's no way I could lift that. It's just too big. Let's say this has 100 newtons, right? It's just too big for me to lift. But, I could use a machine because I would need a huge amount of force. I would need this big, big F, right? But I have a very little F because I'm not strong, right? So I need this big F, but I have this little F. So we bring along a machine, and I'll go through the different types of machines later, and a machine changes this little F to this big F. And there you go. I can lift the boulder, right? So what types of machines would do that? Well, the most common and definitely my favorite and the one you'll see every day of your life for sure is the lever. Let me just go ahead and clear this. Just because this is a pretty important section. So we have types. Types. We have the lever, or the lever, some people say. And I'll draw a little picture of both, of all of them. Lever. And it's kind of like a seesaw, basically. It's called the fulcrum. Then we also have something called the inclined plane. And it's very simply just, you'll actually probably see the inclined plane much more commonly than the lever in everyday life, just because any slope is an inclined plane. But then you can have a pulley, which kind of in its name infers what you would do with it, right? But I'm sure you've all seen pulleys before. Pulley changes direction of a force because you can pull down, you pull down on this rope, on a rope, and you have your pulley up here and the rope goes through. If you pull down, whatever's attached to the rope on the other side goes up, right? So it changes the direction. Remember, machines change the direction or multiply a force. So we saw the multiplication of a force with me trying to lift the boulder, and we're seeing the change of direction with this pulley system. And yeah, those are the three main. There are screws. Screws are an interesting type of a machine. Like an actual screw. And it has the kind of swirls and whatnot. Really, those are a bunch of inclined planes stacked against each other. So all these little guys, are all just small versions of that, essentially. So you don't need to concern yourself with screws, really, and it never comes up. What you really need to focus on are these big three, and they're not hard. You'll get them quickly. So we always want to go back to, because we're all talking about energy. We're talking about forces and distances and directions, and that all leads back to energy because we have work is force times distance, and we have a potential energy and the kinetic energy formulas. And so with all this given information, we know that we're going to be leading back to conservation of energy. Okay? Conservation of energy. So yes, the lever can multiply forces, and this can change direction. But inevitably, all energy has to be the same. All E has, I don't know what that is, has to remain unchanged. Remain unchanged. Net energy, right? So that leads us to this equation. So work input, write it in a different color. Work in must always equal work out, right? And another way to write this is, because we know what work is, force times distance in must always equal force times distance out, right? So pretty simple, because We're always going to be talking about work when we're talking about energy. So let's clear again so I can give you a nice little lever example. Clear. Whoops, that is definitely not black. Okay. All right. So let's draw a lever, and I'll kind of go through the parts with you. We have this little triangular looking thing, and it'll be different on all levers, but that's called the fulcrum. Um, fulcrum. It's basically the point at which the lever sits and rotates upon, or sorry, not rotates, just bends upon. I don't really know how to say it, but the point at which the lever moves upon. And then the most common lever setup looks like this. You have your arm extending like that. And this kind of looks like a seesaw, right? You'd have a big heavy weight here and kind of a lighter weight here. But we're not going to be really using it like that. I mean, you could definitely think of it as a seesaw and you'd get really the same results, but let's look at that diagram with the girl and the boulder. So we have this boulder here. Let's see if I can draw a boulder. Yeah, it's not a bad boulder. And basically, she's trying to move it, and ordinarily she wouldn't be able to move it. She wouldn't be able to pick it up. She's trying to move it up 1 meter off the ground, right? That's how tall she is. She's trying to lift it up, right? And so let's read that little sub-caption. The output force, 80 newtons, is 8 times the input force, 10 newtons, while the output distance is 1/8 the input distance. So that's pretty easy to look at. Let's just finish off the diagram here. So that would be the output force right here, 80 newtons. And then we have our little, this would be distance trying to move it. Sorry, let me, I forgot to draw the other arm here. Not the theoretical arm. This dotted line is kind of the theoretical arm where she wants to move it. And the distance between theoretical arm and actual arm is 1/8 the meter. And the distance between theoretical arm and actual arm here is 1 whole meter. And input force in, is only 10 newtons, right? So basically, what did we do? We multiplied a force, right? We went from 10 newtons. We inputted 10 newtons. And we got out 80 newtons to lift up this big boulder. How did that happen? Well, it's really easy to look at mathematically. Let's just take a look at that equation. Work in equals, oh, I like this color. Work out. I'm going to use this color now. So what's work in? This is the inside. Basically, this girl is pushing down on this lever because she's trying to lift this boulder. So what's the in? What's work in? Well, work in is force 10 times distance 1 in, and it has to equal work out. So that's 80 times 1/8. And sure enough, 10 equals 10, check, right? It works. This machine works, and she can lift this boulder. She can lift it. She multiplies her force from 10 to 80 to lift this big heavy boulder using a machine, a lever. So then let's take a look at just really quickly. If you have little f and big D on the other side of the equation, you must have big F and little d. That's just how it works. It balances out, and it will be an equal equation, or an equal equation. It's kind of pointless. So that brings us back to whole conservation of energy. If 10 equals 10, 10 equals 10, we have that energy is conserved. It's just converted, right? So that's pretty cool. Output equals input. And I think the pulley system, you don't really need to hear from me because it's like you read a paragraph and you got it. But there are those 3 types of levers which are pretty interesting. You have one where the fulcrum is essentially in the middle, and the 2 where the fulcrum's kind of at the end, and there's different weight placements and stuff. So look through that, but there is one last thing that I would like to go through. This is going to be a long video, but let's just do one example problem. This is just, I'm kind of thinking of this off the top of my head, but you know what? Let's make it a word problem, just for fun. If a girl wants to lift a car that weighs, or a car 2 meters, um, using a force of 10 newtons, pulling a lever down 2 meters, what's the output force? What? I just write output. Sorry, that I don't like to write very much with this just because it gets sloppy and not very legible. So I'll just write output. I'm trying to abbreviate as much as possible. Output force. So you could draw that, but I like to look at it just with numbers mathematically. So let's do that whole work in equals work out, and we get, well, what's work in? She wants to lift a car, so that's out. When she lifts the car, that's work out. But she's using a force of 10 newtons, and she's pulling a lever down 2 meters, right? So this is all the in. 10, so we have 10 by 2. Force times distance in is equal to, well, we're missing something, right? We have, she wants to lift a car 2 meters, so we have the distance. We have D. We have F. We don't have F. We need F because output force, right? Times 2. Out, right? Out. Well, pretty easy, right? I mean, it couldn't get much easier than this. The output force must be 10 F out must equal 10 newtons, right? Just, that's a weird N. Just simply because 20 must equal 20, right? Not any other number. So there you go. There's machines. I was hoping this would be the last video, chapter 8, but it doesn't look like it will be because I still need to go over theoretical and actual mechanical advantage and efficiency and whatnot, and probably skip the 8.9 energy for life because that seems a little not important. So yeah, I guess I'll see you in another chapter 8 video.